Alright, here in this video I'm going to fully document as much as I can every single piece of this Stan Meyer's setup here. Just give you a quick on time here. Watch this hydrogen. Just crazy pouring off of there. Alright.
In this series of videos, I document my progress on unlocking the secrets of Stanley A. Meyer. For over a decade, I've studied and replicated the devices of Stanley Meyer, specifically the water fuel cell, a device that splits water into hydrogen and oxygen for use as a combustible fuel. Here, I discuss water fuel cell theory in hopes of connecting with other like-minded individuals to unlock the secrets. This is Stan's Revenge.
Well, let's start with our power supply here. Power supply, this is a variable power supply, up to 30 volts, 10 amps. It's also current limited as well. The other portion of our power supply is this guy here, which is a 12 volt power supply. And all this guy does is provide power to my pulse width modulator. This is my frequency generator here. You can see it uses only 0.002 amps, so 20 milliamps is all I need to add to this equation to get the full amount of power this device is consuming. This way, if this device is on a separate power supply, it kind of isolates it from a lot of noise and things like that. Also a safety precaution too, isolating the controls on a lower 12 volt circuit from an isolated 30 volt, which is powering my transformer. So we have our two power supplies here. This is the pulse frequency generator, Dave Lawton circuit. You can find that online. Basically two PWM circuits, two 555. Let's see if I can peel this guy open here. Basically two 555 chips, two different boards, two 555 timers there, you can see that. Basic circuitry, two PWM controllers piggybacked onto one another so we can adjust the pulse on time and off time, the width, and then segments of these pulses. So we have a burr, pulse, that kind of thing. So these lets me adjust all different types of frequency ranges and things like that. Amp meters here. We have this voltmeter here is attached to our cells all the way from our positive to our negative. We have all these cells wired in series, so this shows how much voltage we have across our entire set of cells. This also goes from the positive from our circuitry here into our cells, showing me how much amperage is actually flowing through my cells. Traditionally, for electrolysis to happen, you have to have many amps traveling through these cells to get production. And traditionally, that creates a lot of heat, a lot of waste energy, consumes a lot of power. You'll see here in my videos and in this demonstration here that we use very little amperage through these cells. So we got those here. This is basically just an on and off switch. Safety on and off to power the actual transformer itself, so kind of extra safety precautions. I've got to have both of these switches on in order for the system to operate. This here is a standard 12 volt, I believe it's a 12 volt step down wall transformer. So like a wall adapter like this guy here. This is a linear power supply, it's grounded. This guy here, we just pulled out one of those. It is not using that capacitor there. It is just a laminated iron core with a primary and secondary on it. Now note, it has been reversed. So I'm using this as the 12 volt input, and the higher 115 volt output is these two wires right here. So it's basically just a step up transformer of a old school style, not a newer switching power supply. It's an older linear style power supply transformer. We have our pulse on and off going into this from our pulse generator here. You can see this is our primary output here. that controls us MOSFET. This MOSFET allows us to take a low power signal and convert it to a higher power signal. So here we have this signal cable going to the G on this one. We have those G, D, and S, gate, drain, and source. So that allows us to draw more power to power this transformer here. But this gates it on and off as a frequency pulses we'll show you here. Now, on the negative of this transformer here, we have a high voltage diode. This is a 2 amp 20 kilovolt Russian diode I got off eBay. Now note, as in Stan Meyer's designs, he has this thing, the diode, on the positive end going into the cell. I've switched this to the negative side and reversed that polarity of it. So the current is still in the same direction. We just kind of put that diode on the opposite rail, if you will, of that transformer. Please note the direction that the power is going negative here from my cells, and then positive has no diode at all. This E-core is not used. There's nothing there. This is basically just this transformer with a diode on the negative side of it. And here we got this going to our amp meter, and that amp meter then translates that yellow one into our cells, which are wired in series. These cells are nothing more than these guys right here. These are 3D printed top and bottom pieces here, as shown in my other videos, how to assemble them. It is a half-inch outer diameter, I believe. But these are 4-inch cells, top to bottom. And you can see perhaps that gap in between them, no more than maybe a millimeter or two. I believe the dimensions of the outer pipes are .065 and the inner ones are .035. Don't quote me on that. It's in my other videos. These are all wired in series, so we have the outer to the inner, to the outer to the inner, to the outer to the inner cell. We have one tube basically inside of another one, and all those cells combined, we wire the inside to the outside, to the inside to the outside, etc. And that way we have them all in series. That is what you'll see here inside of these. These are each one of those is inside of these. So we got basically 6 cells inside each one, series, and then we have all 6 of these wired in series. Alright, I've got this up to 30 volts. And here we go with this again. I'm going to turn this on. You see we have instantaneous production, and then it just starts to puke. So there we go. We have 128 volts across our cell from positive to negative, all those in series. We have only 200 milliamps, 220 milliamps traveling through this system. Now, with traditional electrolysis, like I said, it typically takes many amps to produce this type of gas. In addition, traditional electrolysis also requires that you add some type of electrolyte to the water to make it conductive enough. This is all natural tap water from that faucet right there into these containers. There's no additional material or electrolyte or any type of substance in the water. It is just water and nothing but water. It takes nothing but water to run this system. You really can't see it. There's our bubbler outside there. That's the type of production we're getting. And PVC piping here. We'll explain the cells. These are 2-inch clear PVC off of Amazon. The rest of this stuff is at Home Depot or Lowe's or your local hardware store. 2-inch slip connector. We have a plug at the bottom, a reducer. Reduces it down to 3/4 or 1/2. I do believe I prefer 3/4 over that, like this one here. Splitters, reducers, and two vinyl hose. Each one of these cells also protected by a hydrogen flashback arrestor, which means if there happens to be a spark back that happens to get through this one, let's say if I light this on fire out here just for fun, and a fire explosion travels back through this pipe, this one should stop it. If in the event this one does not stop it, it will make it back to these, but it will stop each cell from exploding. We cannot be safe enough with these. That's why we have one for each set of cells and one at the end point. Here we have additional cells here, or buses, what I call buses, for more individual cells, which we're going to place those in and see what kind of production we get. As far as the frequency goes, this is the waveform I'm getting. Let me pause this. And you can see here, this is the pulse off time where the entire gate is turned off. But if we zoom in on this, you will see, at least to some degree, when we pulse this thing, we have an equal and opposite pulse that's created. And then that snapping action actually brings that pulse down to 0 and actually beyond 0, I've seen in this case. So this is that unipolar pulsing that he's talking about. Bam. And through whatever circuit interaction, when this negative terminal spikes negative, it pulls the positive down with it. So there's a unison event that happens, and it creates this unipolar pulse. If I get rid of number 4 here, you can clearly see that's that kind of pulse. It's that exercising motion from 0 to positive, negative to positive. Yellow here, you can see that is our actual pulse on time. You can see it's really dirty. It gets a lot of flyback. Perhaps an optocoupler will fix that. But in this case, we have on time of, looks like close to 90% pulse on time. So it's a pulse off, pulse off. So that creates that, but we also have these gated pulses where there is a extended off time here, as you'll see, which helps with amp consumption and things of that nature. So here you can see we're pumping 30 volts into the system. We're consuming about 4.4 amps for about 140 watts of consumed power currently. Our amperage has gone up a little bit because I've adjusted this, and it will change over time. We're now at 139 volts across the cell, and just fantastic production. These cells stay cool to the touch. There's no heat generated from these cells. Traditional electrolysis cells, where you hook up just a DC battery to it and just chug a bunch of amps through it, they will get extremely hot, and some are known to melt. That's extreme hazard because there's only less than half an amp going through these. Let's say milliamps going through these. There's no heat generated. It stays cool to the touch. So there it is. In its awe and splendor, we are going to continue working on this to get that production level higher, get the voltage higher to get better production. But that is my Stan Meyer setup in its full specter. Thanks for watching.
This is Stan's Revenge.